So welcome to 4Keys College. So we are launching 4Keys College online seminars, so you can register as a school, you can register as an individual. So you can scan this QR code and you can join our WhatsApp groups so that you get notifications. We'll be answering questions, live questions, making instant videos in this group. So grab this opportunity, it's all for free. So tell a friend, scan the code and join the group. Okay, so we're going to continue with transition metal properties. So transition metals will undergo substitution reactions. We saw that there are various types of ligands that associate with these transition metals, and we also saw that these ligands, when they associate with the transition metal and form complexes, the d orbitals are split into two, a lower energy level and a higher energy level. And when you pass light through a solution of a transition metal complex, some electrons are going to be excited from a lower energy level to a higher energy level, and the energy they require to do so is going to be to correspond to a specific wavelength of light. And so you're going to realize a color which is a result of the white light that passes through the solution minus the energy or the wavelength of light that provides the energy to excite the electrons from a lower energy level to a higher energy level. So basically we're saying these transition metals will form colored solutions. You can go and check the previous video for a greater detail. So let's look at an example here. And we also saw that the color is going to be dependent on the charge, the type of transition element that you have, the type, number 2, the charge, number 3, the type of ligand that you have. So in the above example there, you have your cobalt surrounded by 6 water ligands, and when you add ammonia, it's going to change its color to straw from pink. So this is ligand substitution which has taken place. So your water ligands have been substituted by your ammonia ligands, and this has resulted in a color change. So these ligands will cause a different energy gap between the lower energy electrons and the excited electrons. So that's the theory behind these color changes. Let's look at another example there. So we have our this time we have our copper surrounded by 6 water ligands, and if you add an ammonia there, it's going to change from blue to a dark blue color. So these color changes are important in qualitative analysis. Okay, so let's continue to see some examples here. Cobalt, now you add chlorine, you're going to realize a color change. So here we have a different ligand altogether. Chlorine is a larger ligand compared to water, and you can only fit 4 of these, so the coordination number is also changed there. And if you look at the charge of the complex ion is also changed from a 2 plus to a 2 minus. But the main point here is that when we change the ligand, we are going to see a different color. So we have changed there from pink to blue. Okay, the same occurs here. We have ion and we add chlorine, and there's going to be a color change there. Let's look at the colors. Okay, so our colors, it's yellow. Here we do not see a color change, but of course the shape of the complex ion has changed, but there's no color change there. We still have a yellow color in the case of iron. But we also see that our charge, the charge of the complex ion, has changed. So this is what would happen if you have ligand substitution. Okay, so let's look at some common colors of these complex ions. Okay, so for copper 2 plus you're going to get a blue solution. For iron 3 plus you're going to get a pale green solution. For iron 2 plus you get a pale green. Iron 3 plus you get a yellow solution, and for cobalt you get a pale pink. Now if you add if you add some ammonia or sodium hydroxide, this is what we do in qualitative analysis. You get a pale blue precipitate with copper 2+. You get a dirty green precipitate with your iron 2+. And you also get here your orange precipitate with iron 3+. You get a blue precipitate with your cobalt. Now when you add excess of sodium hydroxide to the precipitate, the precipitate formed for the copper 2+ is insoluble. You can watch my other video where we were talking about how these experiments are done. Okay, then if you add excess sodium hydroxide to the precipitate formed for iron 2+ and iron 3+, these are both insoluble in excess sodium hydroxide. For cobalt, it's also insoluble in sodium hydroxide excess. If you add excess ammonia, so there's going to be ligand exchange there, as you can see in the expression for the complex ion. We're going to get a dark blue solution in excess ammonia. We are going to get an insoluble precipitate in excess ammonia for both our ions, and for the cobalt there we get a brown yellow solution which will turn brown after a while. Okay, so those are the equations that are representing the ligand exchanges that are taking place when you add sodium hydroxide or ammonia. So you can check those equations which are representing the changes that we were talking about. So I want you to take note of ligand exchange that will take place when you add excess of either ammonia or sodium hydroxide. Okay, so those are the equations that are showing the changes that we were talking about in the previous slide. Let's proceed to talk about here stability constant. So some complexes are going to be more stable than others, and we can quantify this using an equilibrium constant that is called stability constant. So we can look at this equation there that involves a complex ion of iron and 6 cyanide ions there. You can see that you can replace all the water ligands in that complex with the cyanide ligands, but there is an equilibrium that is set there. At the bottom we also have another example showing a ligand exchange there. So if we were to write an expression for the stability constant, or the first equation, we're going to say our products over reactants, just like we do with other constants. So that is the expression that you end up with. Okay, you should know that the size of the stability constant tells you how stable a complex ion is. The larger this K stab, the more stable it is. Okay, so let's look at some examples here. You can have this complex ion between copper and water, and you can add chlorine to form that other complex ion. So if you look at the data there, you see that if you compare that product complex ion in that reaction with another complex ion that can be formed between ammonia, water and copper, you realize that the complex ion that involves water and ammonia there is more stable than this complex ion that contains only chlorine. If you look at the K stab there, the one on top has a larger value than the one at the bottom. So if you look at this, so this equilibrium is going to be biased towards your right, okay, because here the complex ion that form is going to be more stable. Let's look at where there's going to be these ions are going to be competing. So if you look at the first equation there, this equation, if I add more water to this equilibrium, then it's going to shift towards the left. remember that complex ion that involves chlorine is less stable, so the equation can move to my left. It's easily reversible. If you look at this, we say this one is a more stable complex ion that I have formed that involves water and ammonia. So what would happen if you added ammonia to this first equation here? If you add ammonia, then some ammonia is going to react with that complex ion that involves 6 water ligands, and so at the end of the day, we are going to have less and less of the complex ion that contains only chlorine, and we are going to have more and more of the complex ion that forms that involves water and ammonia, because that one is more stable compared to the one that contains only chlorine. So this is because of the value of K stab or stability constant. It's larger for the complex ion that contains water and ammonia compared to that contains only chlorine. So the equilibrium mixture is going to have more of the complex ion that contains water and ammonia as opposed to that which contains only chlorine. So this is a case where stability constant can predict for us how much of a product is going to be available in our equilibrium mixture. So I'll see you in another video. Please subscribe to our channel, support us, and join our online platforms so that we can discuss more of A-level chemistry. See you in the next video.